Gotta roll up the sleeves for science. Hey everybody! Welcome back to Sciencing with Abby. I am, again, obviously your host, Abby. I am here with the Research Triangle Nanotechnology Network, or the RTNN, which is a partnership between NC State, UNC, and Duke, and I represent NC State. Go Pack! And today, we are going to do another hands-on, super cool experiment, pun intended, and we are going to make ice cream today. Before I give you the materials and before we go into our actual experiment, I want to first give you some safety tips. So again, everything that we're doing here is perfectly safe. You can find all of these science supplies in your home, but make sure you are working with your science buddy. So of course I've got my science buddy, Mr. Bill here. We never want to do science unsupervised, so just make sure whenever you're doing these experiments, we are practicing being safe and smart scientists. So go grab your science buddy if you don't have one already. Gotta put Mr. Bill back here, hold on. There we go. So now you're gonna need the materials list. Go ahead and pause this video while you go and rummage around and find these things that hopefully you already have in your house. Ready, set, go. 3, 2, 1, and we're back. Okay, so now that you have all of your supplies, let's get ready to do some science. We are going to be making ice cream today, but in order to understand what is going on with this ice cream experiment, I actually want you to think back to my first video with the milk and soap experiment. If you watched it, you'll remember that we talked a lot about solids, liquids, and gases, so the phases of matter. And we also talked a lot about molecules. So molecules are the fundamental Lego building blocks of everything that we see around us. So everything from, this water to the ice to the table to the air that we breathe, everything is made of molecules. But they are too small for us to see with our eyes. So I want you to think about water for a second. Odds are you are familiar with water in every phase of matter that it appears in normal life. Here I've got some, it's cold. We've got some ice, which is solid water. Got some, I have to go get my boiling water, hold on. And we've got steam. You can't really see it, it's steamy, it's a little bit hot in there. And although this water vapor is really cool, it's in a coffee cup and it reminds me of coffee. Steamy coffee is way better than steamy water. Much better. Okay. Happiness. Okay. Like I said, all three of these things are water. They are all made of the same kind of molecule, H2O, so 2 hydrogens and 1 oxygen. But what makes them different from each other? If they're made of the same thing, how come they look and feel so different? I'll bet you already know the answer to that question. It's temperature. They all have a different temperature. So ice is really cold, steam is really hot, and liquid water is somewhere in the middle. But instead of using the word temperature, I'm going to use the word energy. So think for a second, if your mom or dad says that you have a lot of energy, maybe you ate a lot of sugar or got into the stash of coffee maybe, what do you do if you have lots of energy? You run around, right? You go all crazy. Maybe you play outside, maybe you climb a tree or something, whatever. And when molecules have a lot of energy, they run around all crazy too. So when they have a lot of energy and they're running around all crazy, we say that they have a high temperature, which makes sense because steam is pretty hot. It comes from really, really hot water, right? So lots of energy means high temperature. But the opposite is actually also true. So if you have a lower temperature, you're going to have a lower energy because the molecules aren't moving around all crazy. So in ice, super cold, in ice, the water molecules aren't moving around as much as they normally would. They're pretty cold. They have low energy. They want to stay, it's melting. They want to stay where they are. And I'll bet you can guess how this is related to ice cream. Is ice hot or cold? Duh, it's cold. So does that mean it has a lot of energy or a little bit of energy? Little bit of energy, right? So colder means less energy. In order to make ice cream, we're going to have to cool down the original creamy, yummy, delicious components to become a solid. So I want you to take your 4 cups of ice, pour them into your gallon-sized bag. Ah! Don't spill them all over the table like I'm doing. There we go. One more. Okay. Now we have our bag of cream. Well, it's an empty bag now. Also, it's a reusable bag. Save the planet. Save the planet. Okay. So I want you to take your half and half, which I forgot again. This is reminiscent of last time. Okay, hold on. One day I will not forget ingredients downstairs. Half and half. You're gonna take your half and half and pour it into your bag, your smaller baggie. Now you're gonna take your sugar. I'm a scientist. I can scoop sugar. Doing great. Okay, cream and sugar. And also you're gonna add some vanilla. Whatever you do, don't just drink straight vanilla. I know it smells amazing. My brother one time fooled me into drinking straight vanilla because when I was little, I was like, oh my gosh, this smells delicious. Of course I wanna try some. And then I drank it and then got really mad. Anyway, tangent aside, I'm gonna add a little bit more than I'm supposed to because I really like vanilla. Also, I'm just bad at pouring things. Okay, I want you to seal your bag nice and tight. Make sure that it's sealed. And you might want to double bag it. Maybe you want like 2 baggies to like put a baggie inside a baggie just to like make extra sure. Baggyception. All right, here's the ultimate test. Make sure it's sealed shut. Great, that'll work. So I'm just gonna mix it around a little bit, just make sure all the sugar is dissolved. Okay. So we've got our cream for our ice cream, and we've got our ice cream, right? So we should just be able to put the cream inside the ice, and it will cool it down, and it will freeze the cream to make ice cream, right? Let's find out. It's easier if you're able to like somehow lodge the cream like in the ice so that it's kind of in the middle like this, if you can manage it. And you're gonna want to make sure this bag is nice and tight too. Nice and sealed. Don't want any water going everywhere. And now we're going to shake it. And as we're shaking it, you're going to employ your ice cream making super sciencey technique, okay? I'm all about the super sciencey techniques. Also, if you have a towel, you might want to hold it just so that the heat from your hands doesn't melt the ice. And you're gonna shake it. You wanna make sure that you're moving the cream around as much as you can. Here we go. Science. That's enough of that. All right, let's check on our ice cream. See what we got. Oh. What? So the cream is definitely colder, but from what I see, still looks like a liquid. And I don't know about you, but I don't like to eat soggy, liquidy ice cream, because this isn't ice cream. This is just cream. So lame. Wow, that's a bummer. Okay, well, looks like the ice wasn't enough to freeze the cream. Let's see if we can figure out how to turn this bag of cold cream into ice cream. Take it to the North Pole. That could work. Maybe Santa could give us some ice cream. To try and solve this problem, we're gonna do something a little bit weird. I want you to take your rock salts, and it has to be rocks. It's gotta be these kind of nice big chunks. I found actual salt for ice cream, which is kind of fun. So we're gonna use that. And I want you to pour your rock salt into the big bag with the ice in it. Because, you know, salty ice cream, that's delicious. Science. Okay, safety. Anytime you handle the big gallon-sized bag with the salt in it, I want you to hold it with this towel or with, you know, an oven mitt or something. Something insulating to help protect your hands. So I'm gonna mix it around with my towel a little bit. All right. So now I'm gonna take my sealed bag of cream. I don't want any salty ice cream, ew. And I'm gonna put it into the gallon-sized bag with my ice. I'm gonna flatten it and seal the bag. Super sciencey, okay. Done. We're good. I want you to act like scientists. If you're already employing your super sciencey ice cream shaking technique, keep doing that. But I want you to look, is there more or less water in the bag after you added the salt? To me, it looks like more. Remember, thinking like scientists and making observations as we're doing our experiments. And I am actually going to add a little bit more ice to this mixture. So I'm gonna go get some more. Okay. I'm not really gonna measure it. I'm just gonna add some. Fine. Science can be messy, it's okay. The best science is messy in my opinion. Right, this is gonna be a better, just like transfer it. Back with some ice reinforcements. Some nice ice reinforcements, no, just me. I think I'm funny, and that's what matters. So remember, I want you to make sure that you are mixing everything around, make sure you're shaking everything really well. As we're doing this, I'm just gonna do this, and I'm gonna talk as you're mixing all your stuff around. First, I wanna talk about something called the freezing point. The freezing point is a very specific and special temperature where if a certain piece of matter, let's say an ice cube, if, let's say, water reaches 33 degrees Fahrenheit, will it be a liquid or a solid? It's still going to be a liquid, but as this ice is melting in my hands, if the temperature reaches 31 degrees Fahrenheit, is it going to be a liquid or a solid? It's going to be a solid. So 32 degrees Fahrenheit is something called the freezing point of water. It's the exact temperature where the water will turn from a liquid to a solid. Or if you're going from the other way, a solid to a liquid. Just depends. Either way, 32 degrees, that's the magic temperature. I'm gonna stop doing that now because my hands are all wet. So now I want us to check on our ice cream. See how it's going. Ooh, we're getting there. Ooh, we're getting there. It's still a little, it's kind of cold. Mine is still a little liquidy, but I can feel some nice ice crystals forming. All right, a little more. Make sure to leak check every time you close your bag again. Your science buddy will thank you. All right, leak check. All right, we're good. Okay, keep going. Let's say you take your ice right out of the freezer. So let's say your freezer is, I don't know, 30 degrees Fahrenheit. I don't know how cold freezers are. I'm not a grown-up. 30 degrees Fahrenheit, let's say, which is below the freezing point of water. Let's say you take it out and you put it on the counter. There we go. Ice from the freezer on the counter in room temperature. Room temperature is, say, 70 degrees Fahrenheit or so. 70 degrees Fahrenheit, or room temperature, is much, much, much warmer than the current temperature of ice. So the ice is going to warm up, right? And it's going to melt, because that's what happens with ice when you take it out of the freezer and you put it on the counter. So it was 30 degrees Fahrenheit, warms up, warms up, warms up. Now it's 32 degrees Fahrenheit. What's going to happen is a phase change, like we already said. So what state of matter is my water at now? It's kind of a trick question. The state of matter that my water is at is actually two states of matter. Oh, that's cool. Okay. Some of it is a solid, right? Some of it is this ice, but some of it is a liquid. So that's what I mean when I say phase change. And we know that ice just doesn't spontaneously just all melt at the same time, because that would be weird. It is a slow change. The water is going to stay at 32 degrees Fahrenheit until all of the solid water, all of the ice, has melted into a liquid. This system, so when I say system, I mean the mixture of our solid ice and our liquid water, will stay at the temperature of the freezing point. It will stay at 32 degrees Fahrenheit for as long as it takes to completely melt all of this ice. And then once it's all melted, once it's all a liquid, then it will continue to warm up and be room temperature, so say 70 degrees Fahrenheit. All right, so you're still mixing. Let's check on our ice cream mixture. How we doing? Ooh, almost. It's a little watery. You might want to put like a towel down or something. I probably should have mentioned that. Not quite, but we're getting there. Okay, a little more. Seal again. Don't forget your leak check. Make sure. Leak check. Good to go. All right, a little more. Almost there. So we learned about the freezing point of water, which is 32 degrees Fahrenheit. What do you think the freezing point is of that mixture? So the half and half, the vanilla and the sugar. Well, if you can't think of a number right off the top of your head, let's see if we can figure out maybe if it's bigger or smaller than the freezing point of water. So we know from our first experiment that unfortunately failed, that if we just have pure ice, just normal water, it's not cold enough to make the cream go from a liquid to a solid. So from a cream to ice cream. Therefore, do you think the freezing point, the point where the cream will change from a liquid to a solid, is bigger or smaller than the freezing point of water? If you guessed smaller, that's correct. The reason it didn't freeze the first time is because the temperature of this ice here, this 32 degrees Fahrenheit, is too high. It's not low enough to freeze our cream, which is why we added our special ingredient of salt. This seems like magic, but how do we do this? How can you magically make this sciencey mixture just turn colder by adding salt? We scienced it. All right, I'm feeling it. How about you, Alex? Are you feeling it? Are you feeling it now, Mr. Krabs? Okay. Fingers crossed. Big moment. I'm giving myself a drum roll. Oh! Here we go. Boom! Ta-da! I don't know about y'all, but mine has now turned into ice cream. And yours might take a little bit longer, which is totally fine. I'm going to go put this in a bowl and eat it with my mouth. Okay, so I got a bowl, but it's like kind of, I feel like it's gonna be tricky to... Beautiful. Oh, look at this. Amazing, look at this. Anyone else lactose intolerant here? Probably shouldn't even be eating ice cream in the first place. Me! Guess who's eating it anyway? Me! Should I pretend like I'm in a food commercial? Rock salt ice cream. It's not magic. It's science.
I thought you were gonna say it's salt. It's not science.
It's salt. What? Wait, do I have to eat it like I'm a woman in a yogurt commercial? Like...
Yeah. Should be doing it like a pool chair with a big hat though.
I know. Or like frolicking in a field or something. I want to talk about science, but I want to eat this first. Oh my gosh, coffee ice cream duo. Wait. That was a great idea. Okay, I love coffee. So let's say I put a really hot thing next to a really cold thing. when you literally physically put them in contact with each other, they're going to want to become the same temperature. The hot thing will give away some of its heat energy. Remember I said energy is like temperature. So it's going to want to give some of its heat energy to the cold thing. So the hot thing will get a little bit colder and the cold thing will get a little bit warmer, and their temperatures are going to want to meet somewhere in the middle. Let's think about. You're welcome to do this at home as well. You're gonna need a cup of boiling water. I just put a coffee cup in the microwave for like a couple minutes. And you're gonna need some ice. So you're gonna need about roughly equal parts of water and ice. So like a cup of each will be fine, but only with your science buddy around. So we don't wanna be handling boiling water without an adult present. So I've got my. Okay. I got impatient and wanted to finish my ice cream, so I just did that. I'm sad it's over, but that's okay. Chocolate chips, the best idea ever. You can take a coffee cup full of hot boiling water. So remember, boiling is gaseous water, so really, really hot. And pour it in some sort of cup, something. Now you're gonna take your ice and you're gonna put some of your ice into the boiling water. Now we know that normally we wouldn't want to touch a hot cup full of boiling water, right? It's gonna be really hot, it's gonna burn. Just put all the ice in there, put a ton of ice. You can feel the outside of your bowl. If the outside of your bowl isn't very hot, just go ahead and stick your finger in the water. Is it hot anymore? Mine is kind of cold. I also notice that there's not nearly as much solid water, as much ice, as there was when I poured it in there. And you can guess exactly why. So remember when I said hot things and cold things, when they're put next to each other, they want to become the same temperature, so they're gonna meet somewhere in the middle. So in this case, the hot boiling water was really, really hot. When it got in contact with the cold solid ice, they both met in the middle. In our first experiment, the same exact thing happened, where the cream, which was a little bit warm, came into contact with the ice, which was a little bit cold. Their temperatures wanted to do something called equilibrate. Big fancy science word, just means they wanted to meet in the middle somewhere. And when they did that, the ice turned out, I don't know why I'm holding this, turned out to not be cold enough to freeze the cream. So the temperature that they met at in the middle was just too hot. So the cream just stayed a liquid, which was a bummer. But something special happened when we added salt to the ice. On each ice cube that is out in room temperature, there is a very, very thin layer of water on the surface of the ice. Which if you pick up an ice cube, you can probably feel it's gonna be melting, it's gonna feel a little bit slidey. So that's a very, very thin layer of water. And we know that when we add salt, like table salt, when we add salt to water, the salt is going to dissolve a little bit, right? So you've seen this, if you pour some salt into a cup of water, the salt is just all going to dissolve. And the same thing happens on the surface of the ice. So when you have this kind of salt ice mixture, you're actually creating a very, very thin layer of salt water on the surface of the ice. So in this system, right, we have three things. Well, I guess in this system, we have three things. Pretend that there's still cream in this. So just use your brains and imagination. I didn't eat all the ice cream. Okay, this system, there are three things. You've got your cream, which remember, we're imagining that I did not eat all of it. It's still in there. You've got your salt water, remember that thin layer of water that's still on the surface of the ice. And you've got your solid ice cube. So your solid ice cube is still just normal, pure water. There are actually two processes that are happening at the same time when you combine all of these three things together. The first thing that I want you to think about is the interaction between the solid ice and the salt water on its surface, that teeny tiny layer, thin layer of salt water. When you put the ice cube out into the open, it's going to do what it always wants to do. It's going to melt. The process of the ice cube melting actually requires energy. So what I mean by that is in order for the water molecules in the solid ice cube to turn from a solid to a liquid, those molecules have to take in energy to melt. And where does it get this energy from? Because it's not just going to pull the energy up out of thin air, you have to get the energy from somewhere. And it gets this energy from the thin layer of salt water on the surface. The salt water is going to have less energy, which means that it gets colder, right? Because we said things with less energy are colder. So that's process one. As the ice cube is trying to melt, as it's trying to get that phase change, it's going to take energy from the salt water. Second process that happens is between the salt water on the surface of your ice cube and between the cream that I definitely were imagining that I didn't eat. The cream is a little bit warmer than the salt water. So what's going to happen? The heat energy from the cream is going to want to move from the cream to the salt water, right? Because the salt water and the cream want to try to become the same temperature. So as the heat energy from the cream moves to the salt water, the cream is going to get a little bit colder, right? And the salt water is going to get a little bit warmer, and the salt water is going to start dissolving more salt. Here's the special part. Here is why salt specifically was the secret ingredient to us being able to make the ice cream at all. When the salt dissolves into the water to become salt water, so the water just becomes salty, becomes super bitter and hates everything. No, just kidding. What happens is that the freezing point of that salt water actually decreases, which means that the water, the salt water, needs to be colder than normal water in order to freeze. Let's say the freezing point, like of pure water, we already know, is 32 degrees Fahrenheit. The freezing point of the salt water is, let's say, 30 degrees Fahrenheit. So the salt water is actually able to get colder than normal water and still stay a liquid. To look at all of these things all together, you've got your ice melting. It wants to take in energy. It gets that energy from the salt water. So the salt water gets colder because it's giving its energy, its heat energy, to the ice to be able to melt. As it's doing that, like we just learned, the freezing point of the salt water is lower than that of the normal ice. So the salt water on the surface of the ice is actually colder than the actual ice itself. As the salt water continues to get colder and colder, the cream and the salt water are going to want to become the same temperature. So the cream will give some of its heat energy to the salt water, becoming colder. And that process just keeps happening over and over and over and over and over again until you end up with ice cream. I know that that was a lot of information that I just threw at you. Hopefully it was more fun if you were able to eat ice cream while you were listening. But something that's really important here that I want you all to take away, if all of that information was too much, something really important that I want you to remember is note that I never said the words cold energy. I only said heat energy. You're not giving it cold energy. Cold energy doesn't exist. The heat energy moved from one thing to another. So when something gets colder, what we mean is that it loses heat energy to something else. Okay, now I have a challenge for you. So I purposefully doubled the ingredients that I provided you because I want to issue you a challenge, and I want you to think like scientists. I want you to try and think of a variable that you can change in this experiment, and then I want you to see what happens. So just as an example, maybe instead of rock salt, you use something else. So you use table salt, or maybe sugar, flour, I don't know. And then get back to me, and I want to hear how your results changed after you change those variables. And I want you to try to see if you can come up with a reason why the change happened. Try to give me your best guess, And if you don't have a best guess, maybe you're just totally puzzled by the result, let me know and we'll see if we can figure it out together. Great. Well, that's all I've got for you today. Thank you so much for joining me for my cool experiment that joke will never not be funny. I had such a fun time, and ice cream is one of my favorite things in the whole world, so thank you for coming to make some with me. Send me all the pictures that you've got. I would really love to see you all doing these experiments, and if you made any crazy awesome like ice cream sundaes with mountains of whipped cream and rainbow sprinkles and strawberries and hot fudge and all that kind of stuff, send me pictures because I would love to see them. And if, God, I said ice cream, I'm lactose intolerant, I'm not supposed to eat this stuff. If you ended up taking me up on my challenge, let me know what variable you changed and see if we can figure out maybe why the results changed the way that they did. Thank you again, and I hope to see you all very, very soon. Okay, bye.
Come look at this.
They don't think it be like it is, but it do.
You know.
Is that still a meme? Is that still funny? Alright. It would dissolve the salt and the water would become salty.
I was waiting for that.
Please say that. I'm actually gonna... No, I can't do it without laughing. Okay.
Angle down just a little bit. So all of a sudden you look a foot taller.
Did I grow?
Yeah, you look like you're 4'2" now.
Aww. I'm 5'2". Thank you very much. Science.